everyone, and welcome. In the world of big data, we're always up against these two huge, constant challenges. First, there's managing all the data we've already stored, our data at rest. And second, there's trying to process that never-ending flood of new data coming in every single second, our data in motion. Today, we're going to dive into two absolutely groundbreaking technologies. Hey, everyone, and welcome. In the world of big data, we're always up against these two huge, constant challenges. First, there's managing all the data we've already stored, our data at rest. And second, there's trying to process that never-ending flood of new data coming in every single second, our data in motion. Today, we're going to dive into two absolutely groundbreaking technologies that tackle both of these problems in a really elegant way.
You know the feeling, right? It's 3 in the morning, the pager goes off, and you're staring at another failed job, maybe some corrupted data, or a real-time dashboard that's just frozen. It is one of the most frustrating things about being a data engineer. And you start to wonder, what if the problem isn't my code? What if the real problem is the fundamental architecture we're all using?
All right, so here's the game plan. First, we've got to really understand what we're up against. We'll lay out the big problems that plague our traditional data systems. Then, we'll bring in the heroes of our story. Apache Iceberg, which is going to save our data at rest, and this really cool concept called D-streams for our data in motion. And then, at the end, we'll see how these two ideas come together to create what a lot of people think of as the holy grail for data platforms.
Okay, let's set the stage. As data folks, we're basically fighting a war on two fronts, right? On one side, we're trying to manage this messy, chaotic library that is our data lake. And on the other, we're just trying to keep the fragile, super high-speed assembly line of our streaming pipelines from completely falling apart.
I mean, this is the stuff of nightmares for any data engineer. In the batch world, you get things like a source system that decides to add a new column, and boom, every single job downstream just breaks. Or you have two processes trying to write to the same table, and you end up with a corrupted mess. Then you hop over to the streaming world, and it's just as bad. You can have one slow computer in a cluster of hundreds, what we call a straggler, and that one machine can create a bottleneck that brings your entire real-time system to a grinding halt.
So first up, let's tackle that data lake mess. Enter Apache Iceberg. Now, the best way to think about Iceberg is like a super intelligent card catalog for that giant, sprawling, messy library that is your data lake. It's not our placement for your data files like Parquet or ORC. It's a powerful metadata layer that sits on top and just organizes everything.
Now check this out, because this is where Iceberg's first superpower comes in. It's called hidden partitioning. In the old Hive world, you see on the left, you had to be the smart one. You had to tell the system exactly how the data was physically laid out on disk. Your query logic was totally tied to the physical structure. Iceberg says, forget all that. You just write a simple query based on a column, like event time, and Iceberg does the hard work of figuring out which files to read. This is a huge simplification, and it means your code is way more robust.
Next up, Iceberg brings the kind of reliability we expect from traditional databases to the wild west of the data lake. It's called ACID transactions, and the key idea here is atomicity. It means a commit is all or nothing. A change either works completely or it fails completely, and if it fails, the original data is totally untouched. What does that mean for you? It means you never, ever have to worry about two jobs writing at the same time and leaving you with a corrupt, half-finished table.
This one, wow. This is a total game changer for anyone managing a production data pipeline. It's called schema evolution. It gives you the power to add a column, rename one, even change a data type, all without breaking your old queries and, get this, without having to rewrite petabytes of existing data. Your pipelines are finally safe from those inevitable changes coming from upstream. It's amazing.
And maybe the most magical feature of all, time travel. See, every single change you make to an Iceberg table creates a new version snapshot. So if you mess up, like you load some really bad data that messes up your main customer table, you can instantly roll back to the version from 5 minutes ago. This turns a potential weekend-ruining crisis into a simple one-line fix. It is literally an undo button for your entire data lake.
So you're probably wondering, how on earth does it do all this magic? Well, it's all thanks to this brilliant layered metadata structure. Think of it like a tree. Right at the top, a catalog points to the current metadata file for your table. That file keeps a log of all the past versions, or snapshots. Each of those snapshots then points to a list of manifests, and those manifests are what finally point to the actual physical data files sitting on your disk. This separation of metadata from the data is the secret sauce that makes everything else, ACID, time travel, all of it possible.
Okay, so we've got our data lake sorted. Awesome. But now we have to turn to the other front in this war. The super fast but incredibly fragile world of real-time data streaming.
In a lot of traditional streaming systems, everything is tightly coupled. All the computers in the cluster are working together in this continuous, synchronized dance. And that's great for speed, but it's also a critical weakness. One bad actor, a single slow straggler node that can't keep up, creates a bottleneck that can cascade through the system and bring the whole thing crashing down.
And the old solutions for this, man, they forced us into this awful choice. On one hand, you could use replication. You basically run 2 identical copies of everything. Recovery is fast, sure, but it literally doubles your hardware bill. The other option was upstream backup. It's cheaper, but it means when one machine fails, a single replacement machine has to slowly reprocess all the lost work, causing these huge delays in your real-time results. Neither one is a great option.
So how do we get out of this mess? Well, a brilliant team of researchers at UC Berkeley took a step back, and they asked a totally different question. Their idea changed everything. They called it discrete-tized streams, or D-streams for short.
The whole thing starts with this really simple but powerful question. What if we just completely rethought what a stream even is?
And there it is. That's the answer that changes the game. What if we stopped thinking about a stream as one long, continuous, fragile river of data, and instead we see it as a sequence of tiny, separate, and super fault-tolerant batch jobs that just happen to run every second or two?
So here's the big idea, officially. Every second or so, the system bundles up all the new data into a small, unchangeable block. Then it runs a predictable computation on that block, meaning the same input always gives you the same output. It's just like a tiny, super reliable batch job. By breaking the endless stream into these discrete, manageable chunks, you get all the rock-solid, battle-tested resilience of batch processing, but you get it at near real-time speeds.
And this is where it gets really good. Look at the advantages this gives you. If a node fails, we don't need one machine to slowly rebuild everything. No, we can just recompute that one tiny lost batch job in parallel across the entire cluster, which makes recovery incredibly fast. And what about that straggler problem? Well, if a task is running slow, the system just proactively launches a copy of it on a faster machine and takes whichever result finishes first. It's called speculative execution, and it just kills the straggler problem dead.
And you don't have to take my word for it. Here's the proof right from the original research paper. Normally, a job takes about half a second, but when you introduce a slow straggler, that time balloons to over 3 seconds, a total disaster for real time. But with speculative execution turned on, the system fixes the problem and the job finishes in just 1 second. Your performance is predictable again. Just look at that difference.
So we have Iceberg bringing sanity and reliability to our data at rest. And we have D-streams bringing resilience and speed to our data in motion. So what happens when we put these two ideas together? Well, we start getting really close to the ultimate goal, a single unified platform for everything.
Just look at the difference this makes in practice. Instead of needing different, complicated APIs for your batch jobs and your streaming jobs, you just have one simple API. Instead of having to shuttle data from a streaming system over to a data warehouse to query it, you can run interactive queries on both live and historical data right in the same place. We're talking one code base, way simpler logic, and a massive boost in developer productivity.
You know, the authors of the original D-streams paper really said it best. This isn't just about making things a little faster or a little more reliable. It's about fundamentally simplifying how we work with data by finally unifying these two worlds that have been separate for so long.
And that kind of leaves us with a final thought to chew on. Both Iceberg and D-streams solve these incredibly hard problems by creating clever new abstractions that hide all the messy complexity. They handle the hard parts so we don't have to. So it makes you wonder, right? What's next? What's the next great abstraction that's going to simplify our data world even further? That's what we'll all be watching for. Thanks so much for tuning in.